Hello, viewers. In today's class, we are once again going to solve an important problem from definite integrals involving the application of beta gamma functions, right? So here in this class, we'll solve this important integral that is 0 to infinity, and the integrand is x divided by 1 plus x raised to 6, right? So here we'll see how easily we can solve this integral by making use of the concept of Euler's integrals, that is the beta gamma functions, right? So let us start. So viewers, in integration, the method of substitution is a very powerful tool, right? And while dealing with integration, we usually make use of the method of substitution, right? So here, what we will do, we'll also take help of the method of substitution, and let us call this integral as I, right? Now see, here we have x raised to 6. So what we will do, we'll make a substitution, say u is equal to x raised to 6, right? So when we take u is equal to x raised to 6, then x can be written as u raised to 1 over 6, right? So here we have the power 1 over 6, right? So now let us differentiate x with respect to u. So we have dx over du is equal to the derivative of u raised to 1 over 6, right? So here we can use the famous rule in differentiation, that is the derivative of x raised to n is nx n minus 1. Here n is 1 over 6, right? So we have 1 over 6, then we have u, and 1 over 6 minus 1, right? So this is 1 over 6 u raised to minus 5 over 6, right? So now dx can be written as 1 over 6 u raised to minus 5 over 6, and here we have du, right? Okay, now see here the limits of integration vary from 0 to infinity. So accordingly, when we use the method of substitution, we should also change the limits, right? So when x is 0, then the value of u can be calculated from this expression connecting x and u. So u is also equal to 0, right? And when x is infinite, that is when x tends to infinity, then u also tends to infinity, right? So now once doing all this stuff, what we will do, we'll write I in terms of u. So we have 0 to infinity. For x we can write u raised to 1 over 6. For dx we can write 1 over 6 u raised to minus 5 over 6. Here we have du, and now in the denominator we have 1 plus u, right? Because x raised to 6 is assumed to be u. So now let us rearrange the terms. So here 1 over 6 being a constant, we can take it outside the integral sign. So we have 1 over 6. We have 0 to infinity. And now see here we have u raised to 1 by 6. Here we have u raised to minus 5 by 6. So the base are same. So we can simply add the exponents. So we have 1 over 6 plus minus 5 over 6, and in the denominator we have 1 plus u, and this is du, right? So this is 1 over 6, 0 to infinity, u raised to here 1 minus 5 is because the denominators are same. 1 minus 5 is minus 4, and we have 6 here, so this is 2 by 3, right? So we can write u raised to minus 2 by 3, and we have 1 plus u, which can be written as 1 plus u raised to 1, right? Because now we are going to change, or we can compare this integral with our beta function. So viewers, the beta function is defined like this, that is beta mn is given by this integral, that is 0 to infinity. We have x raised to m minus 1 divided by 1 plus x raised to m plus n, right? And here we have dx, right? So this is another form of beta function. The usual form of beta function is given by 0 to 1 x raised to m minus 1 1 minus x raised to n minus 1 dx, right? So this integral is another form of beta function, right? And beta function is also known as Euler's integral of first kind, right? So here we'll make use of this result, that is the first one, right? So if we compare this integral with this one, then we have here the variable u, here we have the variable x, right? And the limits are from 0 to infinity. Here also we have 0 to infinity. So the variable is not going to make any difference, because in integration or in definite integration, this is the dummy variable, right? So now see, here we have minus 2 by 3, and here we have m minus 1, right? So if we write m minus 1 is equal to minus 2 by 3, we get the value of m as minus 2 by 3 plus 1. So m is 3 minus 2, that is 1 over 3, right? And see, here we have m plus n, and here we have 1, right? See, we have 1 plus u. So 1 plus u can be treated as 1 plus u raised to 1. So this is the significance of this exponent 1, because once we compare this m plus n with 1, we'll get an equation in m and n, right? M we have already calculated, this is 1 over 3, n this is 1, so n is 1 minus 1 over 3, that is 2 over 3, right? So n is 2 over 3, m is 1 over 3. So now we can write this integral I as 1 over 6, 0 to infinity, and see, we have u raised to minus 2 by 3, and minus 2 by 3 is equal to m minus 1, right? And m is 1 over 3, so we can write 1 over 3 minus 1, right? And here we have 1 plus u raised to 1, right? And 1 is m plus n, m is 1 by 3, and here n is 2 by 3, right? And this is du. We can also find out the value of m and n by simply making a guesswork, right? Okay, so now see, our integral I, it resembles with this one, right? So I is now equal to 1 by 6 beta mn, right? So m is 1 by 3, and n is 2 by 3, right? So now we have to find the value of beta 1 by 3 comma 2 by 3. So now to get the value of beta 1 by 3 comma 2 by 3, we'll make use of this relation connecting the beta function with gamma function, right? So beta mn is given by gamma of m, gamma of n divided by gamma of m plus n, right? So here I can now be written as 1 over 6 gamma of 1 by 3, gamma of 2 by 3 divided by gamma of 1 by 3 plus 2 by 3, right? So now we have here a 1 over 6 and gamma of 1 by 3. And now see, here we have gamma of 2 by 3, right? So gamma of 2 by 3 can be written as 1 minus 1 over 3, right? So why we are writing gamma of 2 by 3, we'll make it clear in the next step. Now see here, gamma 1 by 3 plus 2 by 3. So 1 over 3 plus 2 by 3 is 3 over 3, that is 1, right? So here we have gamma of 1 is equal to 1, right? So here we have 1. So now we have 1 over 6, gamma of 1 over 3, and gamma of 1 minus 1 over 3, right? So viewers, now see, we have a very important relation in beta and gamma function, which is known as Euler's reflection formula, right? See, gamma of n times gamma of 1 minus n is given by pi divided by sine of n pi, right? So this relation is also known as Euler's relation, right? So here, see, we have gamma 1 by 3. Here we have gamma 1 minus 1 by 3. So if we take n is equal to 1 by 3, we'll get gamma of 1 by 3, gamma of 1 minus 1 by 3, right? So n is 1 by 3. So we have pi over sine of pi by 3, because we are taking n is equal to 1 by 3, right? So we have pi sine pi by 3. Now sine 60 degrees is equal to root 3, that is square root of 3 over 2. So we have 2 pi over square root of 3, right? So the value of this expression is 2 pi by 3, right? So we'll transfer this value to this relation. So I is equal to 1 by 6 times 2 pi over square root of 3, right? So here we have 2 3s are 6. So I is equal to pi over 3 root 3, right? So viewers, the value of this integral is given by pi divided by 3 times square root of 3, right? So by the application of beta gamma functions, we can solve these kind of integrals. Hello viewers, in today's class we are going to discuss one important problem from integrals, right? And in this class we'll solve this important integral with the help of the concept of beta gamma functions, right? So here our integral is 1 to infinity, and the integrand is 1 over x raised to 5 times square root of x minus 1, right? So let us start, and let us first take this integral as I, and here we'll make use of the method of substitution for integration, right? So here let us substitute x is equal to 1 over t, right? So this is the most appropriate substitution here, and here we see that the value of x varies from 1 to infinity, right? So the lower limit is 1 and the upper limit is infinity, right? So when we take this substitution, x is equal to 1 over t, it implies that when x is 1, that is, we can also write this expression as t is equal to 1 over x, right? So when x is 1, t is equal to 1 over 1, that is 1. And when x is infinity, or we can also take this x is equal to infinity as when x tends to infinity, then t tends to 0, right? Because here we have 1 over infinity, right? 1 over a very big number or a large number. So 1 over large number, it tends to 0, right? So now x is equal to 1 over t. So the derivative of x with respect to t is d by dt of t raised to minus 1, because here we have 1 over t. So 1 over t can be written as t raised to minus 1. So this is minus t raised to minus 2, that is minus 1 over t square, right? So dx can be written as minus dt. Taking dt to this side, we have minus dt over t square, right? So now this integral I can be written as when x is 1, we have t is equal to 1. When x is infinite, then t is 0, and dx is minus dt over t square, and x raised to 5 is 1 over t raised to 5, and here we have square root of 1 over t minus 1, right? So now let us simplify this, right? So here we have a negative sign, so we can neutralize this negative sign by interchanging the limits. So we have 0 to 1. Here we have 1 over t square, and then we can take 1 over t raised to 5. That is t raised to 5 to the numerator. We have t raised to 5 over 1, and here we have dt, and then we have square root of 1 over t minus 1, which can be written as square root of 1 minus t over square root of t, right? Okay, so now here we have neutralized this negative sign by interchanging the limits, because we know that this property of definite integrals, that is a to b f of x dx, is equal to negative of b to a f of x dx, right? So if we interchange the limits in definite integrals, then the integral takes a negative sign, right? So now this expression, it goes like this. Here t square get cancelled, so here we are left with t cube, and we have 0 to 1 t cube. Square root of t can be taken to the numerator. We have t raised to half. Square root of t can be written as t raised to half, and then square root of 1 minus t can be written as 1 minus t raised to half, and here we have dt, right? So now we can write 0 to 1. Here the bases are same, so 3 and half get added, so we have t raised to 7 over 2, right? And here we have 1 minus t raised to half, and here we have dt. So viewers, now this integral can be written as I, that is 0 to 1, and here we have t raised to 7 over 2 and 1 minus t raised to minus half, right? So we can take this term to the numerator. Now see, our aim is to convert this integral into the beta function, right? And beta function is also known as Euler's integral of first kind, right? So the beta function is defined as beta mn, and we have 0 to 1 x raised to m minus 1, and here we have 1 minus x raised to n minus 1 dx, right? So now see, here we have 7 over 2, so we can write this integral as 0 to 1 t raised to 7 by 2. 7 by 2 can be written as 9 over 2 minus 1, right? So 7 over 2 can be written as 9 by 2 minus 1. And here we have 1 minus t and minus half, which can be written as half minus 1, right? And here we have dt. So now we can see that this integral is similar to this one, except the variable. Here we have the variable x, here we have the variable t, right? Okay, so now we have m is equal to 9 by 2 and n is equal to half, right? This is n, this is m. So I is equal to beta of 9 by 2 and half, right? And here again we'll make use of an important relation connecting the beta function with gamma function, because we know that beta of mn is equal to gamma of m, gamma of n divided by gamma of m plus n, right? So here we have gamma of 9 by 2, gamma of half, here we have gamma of 9 by 2 plus half, right? So now here also we can make use of one important relation from gamma function. See, gamma of n plus 1 can be written as n times gamma of n, right? So here we have gamma of 9 by 2, right? So gamma of 9 by 2 can be written as 7 by 2 plus 1, right? So if we compare 7 by 2 plus 1 with this one, n is 7 by 2. So we have 7 by 2 times gamma of 7 by 2, right? And repeated application of this result, this formula gives us 7 by 2. Here we have gamma of 5 by 2 plus 1, because 7 by 2 can be written as 5 by 2 plus 1. So we have 7 by 2 times 5 by 2 times gamma of 5 by 2. Again, this is 7 by 2, 5 by 2, and we can write gamma of 3 by 2 plus 1, and we can write 7 by 2 times 5 by 2 times 3 by 2 times gamma of 3 by 2, and we can now write 7 by 2, 5 by 2, 3 by 2, and here we have half times gamma of half, right? Because 3 by 2 can be written as half plus 1. And now in the denominator we have gamma of 9 by 2 plus half, that is equal to gamma of 5, right? 9 plus 1, 10, 10 over 2 is 5, right? And gamma 5 is equal to 4 factorial, right? So 4 factorial is 4 times 3 times 2 times 1, that is 4 3s are 12, 2s are 24, right? Okay, so now here we can write this expression as gamma of 9 by 2 can be replaced by this expression. So we have 7 by 2, we have 5 by 2, then we have 3 by 2 half, and gamma of half, right? And here also we have gamma of half, right? And in the denominator we have 24. So now see, this is 7 5s are 35, 35 times 3, then here we have 2 to the 4, to the 8, to the 16. So we have 16 times 24, and we know that gamma of half is equal to square root of pi, right? So now here we have square root of pi, and again we have here square root of pi, right? So this is 3 8s are 24, this is 35, square root of pi times square root of pi is pi, and this is 16 8s are 128, right? So viewers, the value of this integral is equal to 35 pi over 128.